is apparent by a wide variety of other observations. And I'll tell you a little bit more about that but for now, I want you to keep in mind that when I'm talking about dark matter, I'm talking about a galaxy like this one, which is, let's say, 100,000 light years across. But then there is this blob of dark matter around it, which is maybe around another 5 to 10 times larger in diameter. Okay. And this bigger halo of dark matter, we can't quite see it, but we will see why we know that it's there. Now, it turns out that not only is each galaxy surrounded by this halo of dark matter, but if you zoom out and you look at the universe on much larger scales, so here is a snapshot from a simulation of the universe on large scales. And on this simulation, you can see that this arrow that I have put is approximately 100 million light years across. And on these largest scales, what is shown in yellow are the galaxies. And you can see that these galaxies are like jewels that are encrusted in some very complicated network. But if you pay a little bit more attention, you will notice that around these galaxies, there is this hazy light blue kind of a network within which these galaxies are embedded. This slightly hazy fog of matter cannot be seen using regular telescopes and naked eye and so on, but in this simulation, this represents the presence of dark matter. And this is the dark matter that we are talking about. So the rest of today's talk will be trying to justify to you the following 2 points. Firstly, how do we know that there is such a thing called dark matter? I just told you that every galaxy and clusters of galaxy and this network of structure that we see in our universe is surrounded by an invisible form of matter which clusters and makes these structures, which we call dark matter. Okay, so how do we know that this is true? And then the second part of the talk will be trying to address, okay, if there is such a matter called dark matter, what is it? What is it made of? Okay, so that will be the program for today's talk. So first, how do we know that there is dark matter? And I will give you a large number of techniques by which you can infer the presence of dark matter. But what is common to all the methods, I will give you about 5 different methods, but what is common to all the 5 methods is this mantra, that motion of objects measures the mass around it. Okay, so this is the general principle, that whenever something is moving, it is being affected by masses around it gravitationally. So even if you cannot see those other objects, by carefully measuring the motion of your test particle, you can infer about the masses of the objects that you cannot see around you or around the test particle. So that is the general principle. And now let us look at the application of this general principle in different ways. So first, this is a kind of a warm-up version. So here is a situation where Isaac Newton is standing on the surface of Earth. He has an apple in his hand, and this apple is being attracted towards the center of Earth through the force of gravitation. So the Earth's mass, which is represented here by this capital M, is attracting the apple, which has a mass small m, by this force, which is familiar to all of us. But what this allows us to do, if you know Newton's constant, and if you know what the radius r is, for example, you can simply write down that this mass goes as this r squared by g Newton times the acceleration of this apple as it falls down. Now you can measure this acceleration quite easily by just dropping this apple from a height h and measuring the time it takes to fall, this distance h. And if you just put in the numbers, it becomes quite easy to see that you will find that the mass of Earth is about 10 to the 24 kilograms with, let's say, a height of 1 meter, and the time that it takes to fall is about half a second, and so on. Okay, so this is a simple way to measure the mass of the Earth by just doing a very simple experiment of just dropping an apple and measuring the time it takes to fall, a distance h. So this is how, just from the motion of the apple, I can measure the mass of Earth. Okay, so this is the principle. Now let's apply to much bigger objects much further away from us. So this is the first technique. So what is being shown here in this uh, plot is a part of the sky. You can imagine this as the longitude and latitude on the sky. And you can see lots of dots. Each of these dots is actually a galaxy. And the color of the galaxy encodes the speed with which this galaxy is moving. Now, if you imagine this cluster of galaxies as a gas, which is in equilibrium, then we know from our basic undergraduate physics that the virial theorem relates the kinetic energy, the average kinetic energy of these molecules, which in this case are galaxies, to the potential energy that these galaxies are feeling from all the other galaxies. So the typical velocity, let's say, is v square average. That's the root mean square. And so that's the left-hand side is the average kinetic energy. And let's say these galaxies are being are moving around in in a region of radius r with total mass capital M. Then the potential energy can be written like this. And then if you rearrange this equation, you will be able to estimate this capital M, which is the total mass in this cluster of galaxies, which is given by R times V squared divided by the Newton constant. Now, the Newton constant we know, R we can measure because we know the angular size of this region, and then we can multiply by the distance to this region, let's say if we know using redshifts, and we can measure the root mean square velocity, or in this case, actually the mean square velocity. So by doing so, we can estimate this total mass. And this has been done. And when you do that, in fact, when Fritz Zwicky, who is a Swiss American astronomer who was working at Caltech, when he did that, he found that the total mass in this region was 400 times larger. This is in German, but he says it's 400 times larger than the sum of the masses of the galaxies that you can see. So each of these galaxies has a mass. You can then add up all of those masses, but you find that the inferred mass, this capital M, is almost 400 times larger than the masses that you can see. So this led him to argue that there is a lot of dark matter which is much larger than the visible matter. So the Dunkelmaterie is German for dark matter, and he's saying that it's viel größer, which means it's much larger than Leuchtenmaterie, which means visible matter. So the amount of dark matter in this cluster of galaxies was much larger than that of the visible matter. So this is from his paper in 1933. Now, of course, this estimate was not entirely accurate because there is some amount of mass in a cluster of galaxies that is not visible just because it is not very hot and not emitting light. But nevertheless, this result remains true even today. And it is true that clusters of galaxies have a lot of dark matter, which is truly dark in the sense that it is not like ordinary matter, which is not emitting light, but something else which is more than the visible matter in the cluster of galaxies. And this we will see how we know this by looking at the next four lines of evidence. So the second line of evidence, this was mostly done during the 60s and the 70s, so 1960s and the 70s, is by measuring the orbital speeds of stars in galaxies. Basically, we are aware that in the solar system, as you can see here on the x-axis, you have the radius in astronomical units away from the center of the solar system, which is from the sun. And on the y-axis are the orbital velocities in kilometers per second for the various planets and a few other objects like Pluto and Eris. And we find that the way in which this speed, orbital velocity, drops as a function of r is square root of 1 over r, which is plotted by this dashed line. And this can be easily derived using Kepler's laws. Okay. So you expect this is also you expect this also to happen in galaxies, that as you go away from the center of the galaxy, the speeds of stars, orbiting the center of the galaxy should also decrease in the same fashion. But this is not what happens. In fact, on the left-hand side, I will show you a video of how the galaxies are expected to rotate about their center if Kepler's laws were completely correct. And on the right is what is observed. Okay. And what you will notice, especially if you pay attention to the edges of the galaxies, is that the outer edges of the galaxies rotate a bit faster than the outer edges of this expected Kepler motion. So let's see that. Okay. So if you pay attention to the edges, you will find that the stars are rotating faster on the right hand side video than on the left hand side, which is the one that would be expected from Kepler's laws. Now, why would this happen? This can happen again if there is more mass inside this region. So instead of all the mass being concentrated at the center, if there is more mass as we go out radially outwards from the galactic center, and in fact, even further out from the galaxy, that could explain why the stars are rotating faster, and in fact, why this so-called rotation curve is becoming flat and not decreasing as 1 over square root r. So this was done by many people, but most well known and most importantly by Kent Ford and Vera Rubin. And here is a picture of Vera Rubin while she was an undergraduate student at Vassar College. And this is a picture of this rotation curve. As you can see, as you go away from the center of the galaxy, this curve is not coming down as 1 over square root r, but rather staying almost constant. Of course, nowadays we have hundreds and thousands of such measurements. And so we know that almost all galaxies have matter that extends far beyond the visible part of the galaxy. And then once you go even past the visible part, there are a few stars and they're rotating quite fast. And the only way that these stars, which are much further out from the visible edge of the galaxy, could be rotating this fast is if there is matter here that is not being seen. Outside the visible part of the galaxy also, there needs to be some matter that is not being seen, which contributes to the gravitational force, which then gives this large orbital velocity. Okay, so that's the second line of evidence. Now, the third line of evidence, this is using bending of light. Imagine that we are here on Earth and we are looking at a distant galaxy, which is shown here. And light from this galaxy, as it is trying to go in a direction away from Earth, could get bent towards Earth if there is a very massive object, let's say a galaxy cluster in the middle. And as a result, from Earth, we will be able to, in principle, even see multiple images of this faraway galaxy. We will see the image of the galaxy here, which is the true one. And then if I extrapolate these curved lines through which light is coming to us, we will see other images. This is called strong lensing. And this has been seen, and this was predicted by Einstein's theory of relativity. And using the amount of bending and the magnification of these images, one can actually make a map of how much mass must be there in the intervening region in order for such images to be produced. So this has also been done. And in fact, this is an example of one of those exercises. So what you're seeing here, again, in golden color or in this yellow color are foreground galaxies, okay? And there are also some yellow or white arc-like features that you can see around here and here, these small arc-like features. These are distant stars or like stellar, some sources whose images have been magnified and distorted by some unseen matter in the middle, which has then been colored using false color in this white, hazy way. So this is a map of the mass of the intervening lens that has been calculated by measuring this multiple images and their distortions and their magnifications. And because now we have this map of the mass that is inferred from lensing, we can then compare with the masses of all the visible objects in that region and again verify and infer for ourselves that there is more mass than we are seeing. So this is the third line of evidence. Okay. Up till now, I have given you 3 lines of evidence where we have found that, well, there is some mass that we are not seeing. Then now we will proceed to the final 2 lines of evidence for dark matter, which in my opinion are the most sophisticated and robust and applicable at the largest scales. Not at the scales of individual objects, but at the scale of the entire universe. And here is the idea. It's a little bit subtle, so stay with me for a bit. When we look at the sky, we cannot look beyond a cloud, because light that is coming to us from behind a cloud, let's say the sun goes behind a cloud, the sun becomes invisible because photons from that part are getting absorbed by the cloud. A similar thing happens when you look at the night sky. When you're looking at the night sky, let's say we focus on the picture on the left, when you're looking far away, you are getting light from that far away part of the sky only after some time, because light takes some amount of time to reach us. So if you're looking really, really far away, you are looking at the universe as it was many, many years ago. So if you're looking at a part of the universe that is billions of light years away, then you are looking at the universe as it was billion years ago. Now, it turns out if we believe, as we will argue later, that the universe is expanding and it was hotter and denser in the past, then billion years ago, that part of the sky, that part of the universe was not neutral. It was very hot, and therefore all the hydrogen atoms were ionized, and the photons in that region could not have come to us at the time. All the photons from behind that region are getting scattered and absorbed by the charged ions and the electrons that are in their neighborhood. Only once the universe expanded and cooled down enough that the universe became neutral, the electrons and the protons combined to form neutral hydrogen, only then two photons start coming to us without having significant absorption and scattering. So this point, you know, of time is called decoupling, and this surface, which is, in any direction that you look, there is this curtain beyond which the universe will appear ionized to us because it's very old in our frame. This curtain is called the last scattering surface. Now, you would expect, if you recall your basic undergraduate physics, that this surface, what you would recall that the temperature of this surface, of the region of the universe at this surface, should be about 13.6 electron volt, because that is the energy that it takes to ionize the hydrogen atom. In fact, it turns out that it is a little bit less than that. It is approximately zero point 0.1 electron volt. And this has to do with the fact that there are many more photons, lot more energy in radiation than there are hydrogen atoms. So even though, the temperature has gone below 13.6, the tail, of the energy distribution of these photons is sufficient to ionize the universe. But nevertheless, this is a detail. The fact that there is this last scattering surface with an almost perfectly uniform temperature, no matter which direction you look at, tells us that this picture of a hot Big Bang is true, that the universe was hotter and denser in the past and then became cooler and neutral later on. And in fact, if you measure the energy spectrum of photons that is coming to us from all of these different regions, different directions of the sky, they form a perfect black body, the same black body that was described correctly using Bose statistics. In fact, to the best of our knowledge, this is the most precise black body that has ever been seen. Nobody has produced a black body spectrum from any other source that is better than this. So it's a really, really good description, this black body spectrum. But turns out that if you look at the different directions, although the spectrum is very, very, very close to a black body, it is not exactly the same temperature everywhere. The temperature fluctuates a little bit. And in fact, if you subtract out the common average temperature from everywhere in the sky, you are left with these fluctuations of the CMB temperature, the cosmic microwave background radiation temperature, which is now shown here. These fluctuations are about 1 part or 10 parts in a million compared to the average temperature, which is seen to be 2.7 Kelvin approximately. So the fluctuations are about 10 parts in a million. These fluctuations can then be analyzed using some very simple physics. The idea is this. In the early universe, I just told you that this every little blob of the universe, every part was ionized. So it has radiation pressure. If it has radiation pressure, it pushes outwards. But then it also has energy density, so it has gravitational pull. And so it pulls inwards. So you have two opposing forces. And when you have two opposing forces, you can have oscillations. And this is exactly what happens, is that if there is a part of the universe that becomes a little bit extra dense, just through fluctuations, then it starts to contract under gravity because of this extra density. But as it contracts, it heats up a little bit, and then radiation pressure pushes it out, and then this oscillation keeps on happening, and this sets up waves. These waves can then be analyzed, and I will not go into the details of what you are seeing here, but very crudely, on the x-axis, what is plotted is the inverse of the angular scale, and on the y-axis is how many waves do you see which have a wavelength that corresponds to that angular separation. How much power is there at that angular scale? And we plot this power as a function of angular separation, and we find this curve. Okay. Now the curve, the continuous curve that you're seeing that is passing through all these data points with the error bars, This continuous curve is a theory, and this theory has 5 or 6 parameters. One of the parameters is that how much matter do you have which has gravitational interactions and therefore it contracts under gravity, but does not couple to radiation. So, therefore, does not push outwards. And we find that you cannot fit this curve if you put that amount of dark matter, this matter which does not couple to radiation, if you set that to zero. Okay. In fact, this third peak goes up and down depending on if there is more or less of dark matter. And here is a very convenient video that shows it. So this purple bar is showing you what happens if I increase or decrease the amount of dark matter. It's in, and what you find is that this pattern then changes in the following way, this yellow curve. And for a particular value of this amount of dark matter, this height of this purple curve, purple bar, you will find that this yellow curve will fit this data better. And by doing this, we have determined that about 27% of the total energy density of the universe has to be in the form of dark matter. Okay, so that's the fourth line of evidence. And finally, we can measure, we can observe the position of galaxies around us and plot them. And this is what it shows. And the structure of these galaxies, you will see that there are particular distances over which, if you take a little matchstick of a given size and move it everywhere in this picture, you will find that for a particular size of this matchstick, you are much more likely to find galaxies on both ends of this matchstick. This is basically an informal way of saying that there is excess correlation of finding galaxies at a particular separation, spatial separation. This scale corresponds to the baryon acoustic oscillation scale, and in fact, it has to do with the size corresponding to this first peak. But nevertheless, the details or the subtle features of this distribution of galaxies that you're seeing here tells us that again, we need dark matter, without which these big structures actually could not even have formed. The universe would look far more homogeneous and smooth. These clumps that you see in this picture could not have formed, if there was no dark matter. So to summarize, we have evidence from a variety of different observations at a variety of different length scales. So at the scales of our galaxy, which is the Milky Way, we have things like rotation curve. At the scales of our local group, we have evidence from things like lensing and dispersion of galaxies in galaxy clusters. And at the scale of the observable universe, we have evidence from things like the fluctuations of the cosmic microwave background and the structures in the distribution of galaxies. All of these different observations, and many more actually, together convince us that there is some amount of matter in the universe, in our observable universe and around us, that is not being seen. Okay. Now, that together with the fact that we observe that the universe is expanding and expanding at an accelerating rate, has given us a picture of the universe, which includes not just this thing called dark matter, but something else called dark energy, which I will not tell you more about. But basically, this is our current so-called concordance picture of cosmology, that 68% of the total energy density in the universe is in the form of this thing called dark energy, which I will not discuss today. 27% is in this form of unseen, invisible matter that does not couple to radiation, does not interact with light in any significant way. And then the rest, 4% or so, is made of hydrogen, helium, stars, neutrinos, what else? Okay. So therefore, we come back to our original plan, where I told you that there will be two questions: that how do we know that dark matter exists? And then the next part is that what is it? I hope in this first half, I have convinced you that we know that there is this thing called dark matter in a multitude of different ways, but I haven't yet told you what is it. Uh, is this a good point to take a couple of minutes break and check if there are any questions?
Yes, yes, sir. If you want to that, if
Or if you want,
actually, uh,
or if you want,
but
we can have the questions at the end.
okay, sir. It is also possible. You may
Oh,
continue. Then at the last, we
fine.
can take.
If there are no
Yes,
urgent questions, maybe let's continue and then have the questions at
yeah,
the end. Of course, if there are
yes,
any
sir.
urgent
Yes.
questions, please interrupt me. Please.
Well, then
Actually,
I would like,
uh,
Okay, sir.
I wanted, Vasudev, just
Yeah,
wanted to make a pedantic comment. You said
please.
the CMB spectrum is the best black body in the world,
Yeah,
but it was measured by comparing it with an internal calibration source. So actually, it must be the calibration source that is the best known black body in the world. And in fact, Kobe initially, you recall, in the first 8 minutes of, first 8 days of data, they determined it to be 2.73 plus minus 0.02. But after 3 years, they published another paper where this uncertainty went down by a factor of 20. It was then 2.726 plus minus not 1. And I spoke to John Kogut, and he told me that they had come to understand that internal calibration source better. That reduce the systematic. So, but this is just pedantic. I
no,
mean, yes, you're
thanks
right.
for bringing that up. That's a really fascinating piece of history, I suppose.
Because it's a comparison measurement, right? It's an interferometric measurement. You compare the flux from the internal source versus the sky. That's
That's
why it's so precise. Uh,
yeah.
anyway, just thought I mentioned
Okay.
that.
Uh, all right. I think, are there any other questions or
well,
comments?
I would like to mention that you were
Please.
mentioning about the fundamental constants being in the case of the first one, where the clusters are the gas of galaxies, and you were mentioning about the kinetic and the Newtonian constants and all.
Yeah.
But there is a condition about that the fundamental constants can also change with time when we are calculating with the fine structure constant of alpha for which the atomic clocks have been now manufactured. So what kind of error calculations are in these cases, all the 5 cases for that
Yes.
person, that
So thanks.
perspective?
Thanks. That's a great question. The question is that everything that I told you assumes that certain fundamental constants like fine structure constant or Newton constant are actually constant. That doesn't have to be the case. And yes, sure, one can look into that. In fact, there are people who work on those things. But to the best of my knowledge and with a great degree of certainty, I can say that the observations that I told you about cannot be explained just by varying the fundamental constants. Okay, so you can choose to vary them, and there are limits on how much you can vary them. These cannot be explained by just varying the fundamental constants. So, to the best of our knowledge, the fundamental constants are constant. In fact, they are consistent with being constants, and thus, whatever else I said follows. So, shall we
So
move on?
yes, yes, okay.
Okay, great. All right, so let's move on to the next part. That what is this dark matter? So now the first thing that should come to mind is that maybe this thing that we call dark matter is just a bunch of astrophysical objects that we are not seeing. Okay, it's very likely, right? Because things like planets are cold, they're not very hot. And so they don't emit a lot of light. And if they're very far away and if they're very cold, we will not be able to see them very easily. So maybe there are planets or there are very old neutron stars which have become cold, or this very old white dwarf stars, or maybe even black holes, which we would then say that, okay, then maybe there is nothing too fundamental about this dark matter problem. It's just that there is a bunch of astrophysical objects that are hard to see. Could that be the case? This scenario roughly is called a MACHO, or a massive astrophysical compact halo object. And there are very good reasons to believe that this is not what's going on. There are two arguments. The first argument is that if there are these macho-like objects, these compact objects, they would lead to bending of light around them. And one can look for this kind of bending of light. This is called microlensing. And we don't find enough of those microlensing events. But even more importantly for me, there are measurements from things like Big Bang nucleosynthesis. You measure the amount of how much of each these nuclear elements is there in the universe, like hydrogen, helium, and so on, deuterium. And the abundance of those can be explained very well if you assume a certain amount of matter and a certain amount of radiation. You don't need any dark matter for that. However, if all the dark matter were in the form of ordinary matter which formed these planets and black holes and what have you, then at the time of BBN, the amount of matter would be much more. And then the BBN predictions would not be correct. So the fact that our observations of Big Bang nucleosynthesis yields matches with what we currently believe is the amount of ordinary matter gives further evidence that whatever this unseen matter is could not have been in the form of ordinary matter at an earlier time. Okay, it's a slightly complicated argument, but I hope I made it clear. So then what can it be? So, well, one goes back to basic physics then, particle physics, and one asks that which of the known elementary particles could be dark matter? Well, certainly none of the charged particles, because charged particles interact with photons quite strongly, like through electromagnetic interactions. So it can't be any of the quarks or the leptons. So all of these are gone. That leaves behind uh, as these three neutrinos. Well, photon is massless, so that cannot be dark matter. Gluons don't exist just like that, so that can't be dark matter. The Higgs boson decays very quickly, so that can't be dark matter. The Z boson also decays, that can't be dark matter. The W boson is charged, that can't be dark matter. So what leaves behind is these neutrinos. So they are neutral, and they don't interact with light. They have a mass, but so maybe neutrinos could be dark matter. So that's a good guess actually. And in fact, up until the 80s, neutrinos were considered a very plausible candidate for dark matter. But it turns out that neutrinos, even though they have mass, they're actually very light. And so as a result, these neutrinos travel very fast, almost at the speed of light. And we know that in order to form the structures in these galaxies that we just saw a few minutes ago, maybe a couple of minutes ago, these particles could not be traveling so fast. They have to be non-relativistic. And which is the reason why we know that all of the dark matter, in fact, most of the dark matter cannot be made of neutrinos. Okay? So this is how we know that neutrinos are not dark matter. So that basically kills all our available candidates, and we have nothing that we know of in basic standard physics that could take the form of dark matter. So if you believe in a particle origin of dark matter, you need a new particle. And the features of this new particle are that it has to be relatively stable. It has to basically have a lifetime that's larger than the age of the universe. It has to be basically neutral. It can't couple to electromagnetism in any appreciable way. It needs to be weakly interacting with other particles like protons and neutrons and so on. And it needs to be non-relativistic, which is called cold or slow in cosmological terminology. And of course, anyone who figures out through observation what the origin of this dark matter is, which particle makes up dark matter, is possibly in for a very rewarding trip to Stockholm. So this is, of course, a very, very exciting problem, and many, many people are working on it. And it's a very exciting field with a lot of new ideas. And in fact, the point of my talk today is to, give you a sense of the diversity of ideas and the excitement that goes into this field of trying to solve this puzzle of what is dark matter. So this is a comic strip from the famous comic XKCD by Randall Munro. And this is, of course, a little bit of a joke, okay? Because what it does is it gives you the different masses here on a scale and examples of things that could be dark matter. Not all of these are serious things. Some of them are, but the main point to keep in mind here is that it spans a very large range of masses. To give you a slightly more serious version of this plot is this one. It actually spans many orders of magnitude. It goes all the way from 10 to the minus 22 electron volt to about few tens or maybe even larger solar masses. And one solar mass is about 10 to the 57, if I'm understand GeV or I forget, but yeah, so it's quite large. It's like 70 orders of magnitude or so. These masses stretch, and in each of in this very large range of masses, there are plausible, reasonable candidates for what could make up dark matter. So at the lowest range, these masses are so small that the uh, particle, uh, given the total amount of dark matter, you would need many particles to make up the amount of dark matter, let's say in a galaxy. And then it turns out that it cannot be a fermion, because so many fermions, if you put in a given volume, they are excluded by Pauli exclusion. So at these very low masses, when the number density of dark matter goes up very high, it can only be a boson. And that's one of the favored candidates, is something like an axion. And at these very high masses, let's say solar masses, 10 solar masses and beyond, it is one of the favored candidates is something called a primordial black hole. Now, I told you that normal stellar black holes that form because of collapse of stars, cannot be dark matter, because then these stars at some point of time would have been in the form of hydrogen and helium and so on, and that would have screwed up Big Bang nucleosynthesis. But if much before anything else has happened, much before even stars have formed or BBN has happened or anything, if the density fluctuations in the universe collapse, large density fluctuations collapse to form black holes, then that is an allowed kind of black hole that will not interfere or screw up with measurements that have been obtained afterwards. And that's why primordial black holes can be dark matter. And of course, in between, there are a whole wide variety of other candidates. These should be thought of as heavier cousins of known particles. So let's say we know something like the neutron. You could imagine that there is a particle that is 100 times the mass of the neutron, but does not have strong interactions, does not interact with nuclear interactions and things like that. And therefore, this heavy particle is not being seen, and that's the dark matter particle. So these kind of things are called WIMPs. So broadly, let me therefore focus and whittle down all of these different possibilities into three kinds. So there are very light particles, ultralight particles, which would typically be bosons. There are intermediate mass particles, which can be either boson or fermion. And these are more or less like the normal particles like protons and neutrons that we know, except that they have to be non-relativistic, neutral, weakly interacting, and so on. And at the highest mass end, you have black holes, but a very special kind of black holes, primordial black holes. And the idea then would be to try to look for them. So let me tell you a little bit more about each of these three ideas. So the idea of axions is that there is a new particle, in the periodic table of fundamental particles, which is a boson and which has a very small mass. And the reason it arises has something to do with why the electric dipole moment of the neutron is very small. Okay, so this I will not go into the details, but this is called an axion. But there are other examples of what can be a light boson, but for now, I just mentioned this axion. Let's move on to this middle candidate. It's called WIMP, and one of the most widely studied candidates for dark matter is this idea. The reason is that this kind of a particle very easily produces the observed abundance of dark matter. And that has something to do with chemical freeze out. Let me skip over it for now because I don't want to go over time, and move on to a related idea. So the amount of dark matter that you see around us, for example, could also be determined by, well, maybe there is dark matter and then there is anti-dark matter and they annihilate, and whatever annihilate becomes just, let's say, energy in the form of photons, let's say. But there is a little bit more dark matter than anti-dark matter. And this little bit of excess is what we are seeing today as dark matter. So this is also another very popular idea called asymmetric dark matter. So there are all these different ideas, and particle physicists and astroparticle physicists write mathematical models for these kind of ideas, and then they compare these ideas with various observations, which I'll tell you in a minute. And then the third idea I just told you about, these primordial black holes. So now the question is that we have all these ideas. It's not enough to have this idea. The real fun and the real game here is to check these ideas using observations. You have to be able to do experiments and observations that test these ideas. And if the observations tell you that this idea does not work, or that this idea only works within certain constraints, that tells you a little bit more about what dark matter cannot be. And therefore you start looking at the areas or the regions where dark matter could be, and so on. So let's talk a little bit about it. One of the most uh, popular ways of looking for axions, this very light dark matter, is using things that resemble radios. So it turns out that the axion particle couples very, very weakly to two photons. And so one of the photons could therefore be a magnetic field. And so you have a magnetic field in the lab, and an axion comes to the lab from outer space and interacts with this magnetic field and creates an electric field, which is the second photon. And this created electric field manifests in your radio as a little voltage. And then you measure this voltage, and by trying to measure this, you can try to look for this flux of axions coming to you, for example. This has been tried, and non-observation of such signals then tells you that you don't have axions in a certain mass with a certain abundance and a certain strength of interaction with the photons. So this is how this field proceeds, that you start putting what are called exclusion limits on the masses and the couplings of dark matter candidates, in this case axions, and therefore by excluding certain parts of the so-called parameter space, you learn a little bit more. Similarly, you can do it for more heavy dark matter candidates, where this dark matter candidate that's in the galaxy, so this is our galaxy, we live in its halo, and a particle can come and interact with, let's say, a proton that is almost at rest in the lab. Okay, and when it comes and hits this proton, then the proton will recoil like a billiard ball. Okay, and by measuring how many protons are recoiling in a very cooled down sample kept very deep in a mine where nothing else is reaching, we can again try to look for these dark matter particles. This is called direct detection. This has been going on for many decades now, and many, many orders of magnitude improvement in the rate of interactions of these dark matter particles with protons. This has been studied, and all these colored regions are couplings as a function of the dark matter mass that are now ruled out, that dark matter cannot be something with a mass of 100 GeV and a coupling that looks like this. That is already excluded. Of course, it is allowed to be somewhere here, that you can have 100 GeV dark matter particle, but with, let's say, some small coupling, which is in this white region. Okay, so I'll not tell you more about it right now, but this is another class of experiments. As the third type of experiment that you can do with WIMPs is that sometimes you can have models where these dark matter particles can collide with each other and give rise to particles that can be seen by our telescopes, let's say electron positrons or photons or what have you. And then what happens is that these two dark matter particles interact in this galaxy, let's say near us, and when they annihilate, they give, say, an electron positron, and one of those charged particles can then be detected by one of our detectors, maybe on a satellite. And by trying to look for these annihilation products of dark matter, you can also search for dark matter. So this has, of course, been tried using a variety of different sources for dark matter. So the sun, the Milky Way, nearby galaxies, and what have you. and using a variety of messengers. Whether you are looking for charged particles like cosmic rays coming to you, or whether you are looking for neutrinos, or maybe even high energy photons. All of these have led to a wide variety of constraints on dark matter. And we know that if dark matter is in the form of this WIMP-like heavy particle, it cannot have certain cross sections or certain rates of annihilation. So, unfortunately, we have not detected dark matter yet, but we have produced excellent constraints on the kind of dark matter that could be. There is, of course, the possibility of producing these dark matter particles in a collider like LHC, for example. Unfortunately, that has also not succeeded. So, which brings me to the last candidate, which is primordial black holes. And to be honest, over the last 5, 6 years, a lot of excitement has grown uh, for the possibility that this black hole is in fact made of primordial black holes. And this possibility is indeed open, especially if the black holes, these primordial black holes, are of this mass. So, what you're seeing on the x axis here is the mass of these black holes in grams, let's say, measured here. And on the vertical axis is the fraction of the total amount of dark matter that can be in the form of these primordial black holes. And these colored regions or the shaded regions are again excluded regions which cannot be there. And what we have found in recent times is that these regions which are colored are excluded because if primordial black holes existed at this very low mass, then they are very hot and then the Hawking radiate. And then we could see the products of this Hawking radiation from the black holes. We don't see that. And so therefore we know that if at least some appreciable fraction of dark matter is in the form of primordial black holes, it's certainly not in this region because then we would have seen it. And similarly, these shaded regions are ruled out by other observations. But this white region, which actually corresponds to masses which are similar to an asteroid, this is still not ruled out. And it would be very interesting to come up with observational strategies that can close this region or produce some constraints in this region, which would then tell us that, okay, well, we either discover primordial black holes in this with these masses, or we say that no, primordial black holes also cannot be dark matter. So this is, of course, an open question and one of the current topics of research in this field. So with that, I would like to stop. That's all I had to tell you. So this is a very exciting field, and I encourage and invite many of the students attending the lecture, to read more about dark matter and to learn more about it. And if interested, explore this very fascinating area. So here is a summary of what I told you today. That we have a lot of evidence for dark matter at all scales, but we don't know what is the fundamental nature or the particle identity of this dark matter that we have seen. There are a lot of theoretical ideas. I told you about three of them. So very ultralight dark matter, which can be like axions, which is a kind of a boson, or normal particle dark matter, which can be fermions or bosons, or it can be very ultra heavy, which, for example, can be a certain kind of black holes. And there are ways of looking for these different kinds of black holes. And depending on what is your assumed type of dark matter, what do you think is making up this dark matter, you have to conduct a variety of different experiments to look for them. Not in this region, because then we would have seen it. And similarly, these shaded regions are ruled out by other observations. Sorry, there is some. But this white region, which is very ultralight dark matter, which can I can hear my own voice repeated to myself. I think, okay.
Oh, sorry, sir. Sorry, sir. I was just checking if there are any questions in the chat box. Sorry for
No,
that.
no worries. All right. So I told you that there are these ideas for what dark matter can be, and there are some, ongoing efforts to look for this dark matter, and it's a very exciting ongoing effort. It's uncertain. But it's very challenging, and especially for students and young researchers who are interested in these kind of things, this is a very exciting time to be working on this area. So with that, I will stop. I thank you all for your kind attention, and thank you for having me once again.
Thank you so much, sir. was really informative and compact information that we gone through actually in your talk. And now I would like to request if anyone ask any questions to sir directly from the participants. We have here Dr. Tomal Kumar Mukherjee. He is associate professor here, sir. He is actually in the same field. So I would like to welcome Dr. Mukherjee for this question session and discussion session. Dr. Mukherjee, are you here?
Am I audible?
Yes, I can hear
Yes, you are audible.
Yeah, I can't see any question on the chat in the chat box. Maybe students, if you feel to ask any questions to the speaker, feel free to ask. Uh, Meanwhile, maybe I start with asking you some questions I have in mind. So, suppose, for example, in these axions, these are also used to model the QCD phase transition, for example. So, is there any bound on the mass of the axions? Uh,
Okay.
because if it is in the range of what LHC is probing, the energy range, should it be higher than the energy range that LHC is currently now probing, or?
Yeah. Okay. So I am not very aware of what kind of constraints LHC produces on axions. So let me go back a little bit. So the way axions are connected to QCD has to do with the theta term in the QCD, which is that uh, you can write a term that is that has to do that actually
Phase
violates.
anomaly.
Yeah, so it's FF dual in okay, so let's put it this way. So in electromagnetism, the field tensor or the tensor that we write down is F mu nu, right? Which actually, if you write in terms of electric and magnetic fields, is E square minus B square. We do not write a term that is E dot B, right? Why? Because E dot B is a term in the Lagrangian, it would violate parity. And we know that electromagnetism does not violate parity. So we don't write that. Similarly, in QCD, you can write a term, which is GG dual, which is exactly the same as E dot B. Okay, but just in the case of QCD. Now, again, the question is, why do you not write that term? One of the ways in which you would not write that term is if GG dual were coupling to a field called the axion, okay, and this field landed at the bottom of a potential where its value became 0. So that is the explanation for why there is no, CP violation in QCD. Great. But then the prediction is that if this field is at the bottom at 0, it can oscillate around the bottom, and these oscillations are the axions. Okay. These oscillations correspond to a mass typically that's very, very small, much smaller than an electron volt. In fact, what I'm showing you here is that these masses are like micro to milli electron volt in this range. You see, this is mass of the axion in electron volt. Okay. And for values around 10 power minus 2 electron volt is where I would, so the QCD axion corresponds to this mass, which is on this x-axis, and the coupling, which is shown on the y-axis, and the QCD axion would be given by, I don't see where it is shown. I imagine, does this plot have it? Let's see. I don't see it here. So I think this plot does not show the QCD axion, but basically I imagine it's this red line. Okay, this red shaded diagonal line corresponds to the QCD axion for a particular choice, the KSVZ. Now, all these different experiments, as you can see, these different other colors, shaded regions, they are probing different combinations of mass and coupling. And you can see most of this red dashed line, this red diagonal band has actually not been probed, although we have started probing it. LHC is not the experiment that is probing it, but there are other experiments. So that's the state of the art.
Thank you, sir. So there is another question from our audience. So so I'm just reading out the questions he has written. So as you previously explained that there is a halo of dark matter around galaxies, doesn't that also mean that there is dark matter all around us at this moment? Hence, even localized experiment can use to detect and infer evidence and effect of dark matter around us. My question summarized, why should we only look at the sky to infer the existence and effects of dark matter? Does the evidence also point that existence of dark matter all around us locally?
Okay, that's a great question. So just to summarize the question in very brief, I told you that there is dark matter on the scales of galaxies and larger. But I did not tell you that there is evidence for dark matter on, let's say, the solar system scale or even smaller, let's say in my room. I don't mean to claim that there is no dark matter around us. Possibly we are swimming, in a sea of dark matter, but we have not detected it yet. Okay. So there is absence of evidence, but there is no evidence of absence. Okay. So there is absence of evidence of dark matter on these scales. But so we haven't quite detected. But that does not mean that we are not trying to detect. All these experiments that I am talking about are experiments being conducted on Earth in a lab. And they depend on this assumption that there is going to be this sea of dark matter, that is going through us constantly. And we will therefore detect some interactions of this dark matter that is around us, in our rooms, where this experiment will be conducted. But this will be very rare for two reasons: that the interaction is very weak, and secondly, the size of our experiments is relatively small. When we talk about interaction of dark matter with galaxies, the mass that is contained in the whole galaxy is very large. So, these interactions, even though when they are mediated by gravitational force, which is very weak, they're still these interactions are significant. But inside the lab, we are working with very small objects. And there, the amount of interaction can be very small because the number of targets is small. So because of the weak interactions and small number of targets, it is very difficult to look for dark matter. This is why this field is so challenging. But we are doing it, we are trying. All these experiments are explicitly trying to look for dark matter in the lab, with the exception of these ones that I told you, which is this annihilation in the galaxy. So this one is something called indirect detection, where the dark matter interacts with another dark matter, somewhere far away, and you're only probing the products. Here, you are not assuming that the dark matter is in your neighborhood, in your lab. But for this one, where dark matter comes and has to hit a proton in your lab, you do need dark matter in your local neighborhood, and that's precisely what is being probed.
So before going to the next question, so let me pick up this point. So suppose, for example, you have this scattering of dark matter or collision of dark matter, and they are producing known particles. So when you detect from the Earth, should we expect the isotropic distribution of these excess particles, or there will be anisotropy as well?
That's a great question again. And in fact, this is exactly how we would like to distinguish a signal of dark matter annihilation from all the other signals. If you look at space, there are charged particles, neutrinos, and photons coming from all sorts of directions. How do we know that what we are seeing is coming from dark matter? It could be that there is a star there, or maybe there is some black hole there, which is, producing charged particles. How do we know that the charged particles that we are seeing here in this picture are coming from dark matter annihilation? So one of the ways in which you do this is you map the flux of these incoming particles as a function of coordinate from the center of the galaxy. And we know how the amount of dark matter varies from the center of the galaxy because we have measured the rotation curves. And we try to correlate if the intensity of this radiation that we are observing is in fact correlating with the density profile of dark matter that you expect. In fact, this is exactly what has been done during the decade, let's say from 2007, 8, all the way until 2017, 18. So these experiments have been ongoing. And to be honest, there are in fact hints of such radiation from, let's say, the middle of the galaxy. If you look at the center of the Milky Way, we do see some unexplained radiation that is in fact consistent with the abundance of dark matter in the galactic center. But it is also consistent with an abundance of certain astronomical objects like pulsars in the galactic center. So we are in this situation where we have a signal which in principle could be from dark matter, but we are not claiming currently that it is dark matter because we have not sufficiently strongly ruled out the other possibilities. But the way in which we proceed is precisely the way that Dr. Mukherjee described, that you look at the morphology of the signal. Similarly, you can look at the energy spectrum of the signal and other things. These are the tricks that are used by observers to identify the origin of the signal that they're seeing. Great question. Thank you.
Thank you, sir. So we have another questions from Gahun Chattopadhyay. So the question is, what do we know about the coupling of dark matter with other fields other than electromagnetic fields?
Okay. So the question is, what do we know about the couplings of dark matter with other particles, other than electromagnetic? So what we know,
Other than the electromagnetic.
yeah. So we know that, okay, all current data is consistent with dark matter not interacting with any other particle except through gravity. Okay. So we have evidence for dark matter interacting with everything through gravitational force. This is how we know that there is dark matter. But other than that, there is no evidence for any other interaction. In fact, it can be zero, which is in fact one of the most worrying and difficult and challenging parts of this field of research. That if the situation, if nature is very unkind and has chosen to have dark matter have no interaction with our other particles, then none of our experiments will ever succeed. We will never know what this nature of this dark matter is. So this is indeed a problem. There are some caveats to this. There's a little bit more that one can do, but broadly, this is indeed a very valid issue and a valid concern that if indeed dark matter has no interaction, it will be basically impossible to find out its origin. So in the field, this is something that people worry about.
Thank you, sir. So I'm sure Professor Bhattacharya is having some question in mind. So Professor Bhattacharya, would you like to ask any question?
Thank you, Tamal. Thank you, Dr. Dasgupta, for very, very nice talk. I have no question, but I just want your comment. There are lots of work going on when the neutrino and the sterile neutrino can be the possible candidate for the dark matter. So what is your comment on that? You are just, I just want some comments from you.
Yeah. So is your question that can sterile neutrinos be dark matter? Is that the question?
Yeah.
So, okay. So for the students, so
And
we know that there are.
what is sterile neutrino is to the students also.
Indeed. So thank you for that question. So we know that there are these particles called neutrinos. These are light neutral particles. These are particles that have mass that are less than 1 million times the mass of the electron, and they have no charge. These are active neutrinos. These are produced in beta decays. When neutron decays to a proton and an electron, it produces an electron antineutrino. So these particles we have detected, we know that they are there. Now, there are theories which predict that there are neutrinos other than these three neutrinos. Okay, and these other neutrinos are even more weakly interacting than the normal neutrinos because they don't even interact with what are called weak interactions. This is W and this Z boson in particular. Okay, W and the Z boson, and these so-called sterile neutrinos, these additional, this fourth or fifth or sixth neutrino, these hypothesized, imagined neutrinos are called sterile neutrinos. And they're called sterile because they don't interact with W and Z bosons, which are responsible for weak interactions and radioactivity. So these sterile neutrinos, we don't know if they're there or not. And if they're there, we don't know what their mass should be. So again, just like dark matter, it is a hypothesis, and one can test this hypothesis by doing a variety of different experiments and observations. There are certain parts of this sterile neutrino parameter space for a certain mass and a certain coupling. These sterile neutrinos are believed to be consistent with dark matter. So for example, if these sterile neutrinos have a mass of about few kilo electron volt, then there are theories that say that these sterile neutrinos can be dark matter. These theories are currently under a little bit of pressure because of observations of X-rays from certain galaxies, non-observation of X-rays from certain galaxies, which are predicted if these sterile neutrinos are indeed all the dark matter. It's again an area of frontier research. Broadly, yes, sterile neutrinos of keV mass can be dark matter, but in detail, there's a lot more work that needs to be done to make a more definitive statement in this direction.
Okay, thank you.
Okay, thank you. So I can see Shayanjit Bishas raises his hand. So Shayanjit, can you please unmute yourself and ask the question directly to the speaker?
Yes, coming from a sterile neutrino question of what it was, I would also like to know what is actually QCD transitions.
Sorry, I couldn't hear the question. Can someone repeat that for me?
What is QCD transitions?
Okay, so to be honest, I did not talk about QCD transition here at all, but very quickly, QCD is a theory that describes the dynamics of quarks and gluons. These are elementary fundamental particles that are believed to make up protons, neutrons, and other particles which we call hadrons. Okay, baryons and mesons are made of quarks, and these quarks interact through gluons. Now it is this theory called quantum chromodynamics, QCD. It's a theory that describes the dynamics of these quarks and gluons. And one of the most interesting features of this theory is that when these quarks and gluons are moving with large relative momentum, they are free. Almost they are like free particles and they interact only a little bit. But when these quarks, let's say, are interacting with each other through very small relative momentum, then they interact very strongly and they get bound. In fact, the theory predicts that the quarks never actually survive independently and solitarily outside just like that. They're always confined inside baryons and mesons. They're always packaged, just like how electron, proton, and neutron are packaged into an atom. Similarly, quarks and antiquarks are packaged into mesons, and three quarks are packaged into a baryon. So the proton is made of three quarks, UUD, and the neutron is made of three quarks, UDD. In fact, to be precise, there are something called C quarks and so on, but let's not go into those details. So our known hadrons are made of these quarks, and these quarks interact through QCD. Now, this QCD phase transition is a statement that if you take these baryons, let's say protons or neutrons, and you put them in a box and you heat this box, basically you give a lot of energy to this box, there is a particular temperature above which these protons and neutrons will melt, and you will not have the quarks and the gluons completely confined inside these baryons, but they would form a plasma. It's called a quark gluon plasma. This has in fact actually been seen, and we know that the temperature at which this happens is around 140 MeV, capital M, mega electron volt. So if you take a bunch of protons and neutrons and you heat them to a temperature larger than about 150 mega electron volt, the protons and the neutrons melt and form this plasma, this sea of quarks and gluons. That's the QCD transition.
Okay.
Okay, thank you. So one final question. So it's asked by Qazi Islam. So he's asking, just a minute. Could dark matter be an emergent property of fields that interact via many-body forces?
Yeah, so I'm not very aware of. So the question is that does dark matter have to be a fundamental particle, or could it be some pseudo particle, just like the way we have phonons inside crystals? We say that there are degrees of freedom, like vibrations, which we can quantize and we can think of like particles, which do everything exactly like particles, but are not real particles. They are just emergent properties. The crystal vibrates in a certain way, and this vibration is then mathematically represented like a particle called a phonon. So the question is that can dark matter be something like this, which is not a real particle, but rather an emergent property of something? I am not aware of any well-formed theories which successfully describes all available cosmological data on dark matter by making this assumption. So in principle, it may be possible, but I am not aware that this has actually been shown to be true by anyone.
Thank you very much, sir. Thank you very much for patiently answering all the questions. I'm sure that there are infinite number of questions people having in mind, but due to time constraint, we should stop somewhere. So I think this is the best place to stop. So over to Papia for final remarks.
Thank you. Thank you so much, sir. It was really, really a good session, interactive session. And I can tell you that there is number of questions still in the chat box, but we couldn't ask actually. Sorry, participants. But okay, maybe Dr. Dashgupta will be happy to answer. Maybe if I send these questions to you.
Yes.
Right, sir. Okay. And I want to say that there is just 1 hour, but we got 1.4K, 1.4K views in Facebook Live. That is really nice. In this time, this much people are seeing our live. Thank you so much, sir. So actually now we come to the conclusion of this enlightening session, and it is my great privilege to extend a heartfelt vote of thanks on behalf of Department of Physics. So I would like to express our deepest gratitude to our esteemed speaker, Professor Vasudev Dasgupta sir, for his insightful, inspiring lecture. Your expertise and engaging discussions have truly enriched our understanding of this fascinating topic and inspired our this young minds and as well as us to explore the vastness of the theoretical physics. We are really thankful, and I would like to inform you that our dean sir, dean of School of Basic Applied Science, Professor Bimal Kumar Sarkar was there initially, but due to some work, he has to leave. He extend best wishes to you and a gratitude as you have accepted this invitation. Come here to deliver this talk. So for that, thank you so much.
I have
And obviously,
Yeah, I have to add one line. Sometimes we can have you in our campus. We'd like to
Sure.
have the Ramat
Yes, sir.
campus, yes.
Yes, sir. We are really waiting that whenever you will come to Kolkata, just let us know, and we can
Be happy.
interact directly with you. It would be very nice actually. And I think Aparajita madam will be very happy that I mean, I can feel now that as a teacher, whenever your students is in front of you in this position, it is really proud moment for us.
Okay.
It's really good.
Well,
I
it's
just,
a pleasure. It's a
yeah,
pleasure.
right. Made us proud. Your alma mater proud, of course. HOD Momita, they will like to say something to Professor
I
Dasgupta.
would only like to say, ma'am,
Yes.
it was a wonderful talk. Thank you so much.
Thank you for
I'm
having me.
sure everyone has enjoyed a lot and learned a lot.
Thank you for having me.
Thank you.
Yes, sir. Thank you so much. Last, I just want to thanks, like I would like to extend my sincere thanks to our Honorable Chancellor Sir, Vice Chancellor Sir, respected Dean Sobers, Professor Bimal Kumar Sharkar, respected HOD Physics for their constant support and encouragement. I would like to thanks faculty members, my colleagues, our students, and our wonderful audience. I should appreciate you because you have interacted at a lot today, whose presence made this event truly meaningful. And with this, last but not least, thank you so much, our IT team, especially Mr. Ranobrato Chanda, and also we are grateful to Mr. Arnav Basu branding team for this nice digital flyer and all the technical support. And with that, I formally conclude the session. And any participant, if you want to add anything, and if Dasgupta sir, if you want to add anything at the end moment, then we can conclude that.
No, I just want to say thank you to everyone, and it was a pleasure being here.
Thank you. Thank you so much, sir.
Well, I would like to just add that is there a
Yes, yes.
repository of the previous 3 lectures?
Previously lecture, yes, it is available in Facebook Live.
Well, other than Facebook, actually, I am only mostly restricted to YouTube only.
Okay, YouTube, I think.
I think
YouTube.
in
I don't know,
university YouTube page, you can also find it.
Yes.
Okay.
You can write me. I can send you the link. Even
Yeah.
I
Okay,
think
then I will.
already I mailed you the link.
Okay,
I
then. Okay,
mailed
then
you
I
the
will do
link.
so.
All yes,
It's available. In YouTube, it's available.
yes.
Okay.
Okay, so with that, I formally conclude this session. Wishing all of you a wonderful day ahead. Hope to see you soon, maybe in this another event organized by Department of Physics at Amas University. Thank you so much, all
Thank
of you.
Thank you so much. Okay, then we can leave, Papia.
Yes, ma'am. Yes, ma'am. Okay. I can sharing the for the participants. I can share the feedback link.
Thank you, ma'am.
Yes, I can share the feedback link. Please. You can, if you feel it, you can generate a certificate. Okay, it is available in the chat box.
Tapia, then I'm leaving.
Yes, ma'am, you may leave.
Okay, thank you so much.
Thank you, thank you.
Excuse me, ma'am, is the link for certificate generation given?
Yes, it is available in chat box. See, we have shared. If you fill it, certificate will generate. And if there is any technical issues you face, just mail me, or you can tell me through WhatsApp. This is my WhatsApp number as well, which is sent.
Ma'am, I can only see the feedback from here. I may be mistaken. I have already filled out the feedback form. Okay.
Yeah, this one.